So welcome you back to today's module. So what we were discussing in last couple of lectures was how to compare different estimators asymptotically. Asymptotically in the sense that as sample size goes to infinity. So the first approach which we saw or which we studied was the limiting risk approach. The idea behind limiting risk approach is that if you consider any reasonable estimator delta n, then limit n going to infinity of risk of delta n is always 0 for every theta. So any reasonable estimator would have risk 0 as sample size goes to infinity for any parametric configuration. So normally there are more than one estimators for which this condition is satisfied. What you try to look for an estimator which converges, whose risk converges to 0 at a much faster rate. And then among estimators which have the same rate of convergence, you can think of estimator, or you may think of preferring an estimator which has smaller limiting risk. And that led to the concept of a limiting risk approach, and then we talked about limiting risk efficiency of one estimator relative to the other. Now, one disadvantage of limiting risk approach is it assumes that risk exists, which is equivalent to saying that at least the two movements exist if you are considering the squared error loss function. So it assumes that the first two movements of the distribution exist. So it is restrictive in that sense. So if you are ensured about the existence of a movement, this approach is perfectly fine. But that may not be the case in many situations. So another approach which doesn't require existence of movements is we talk everything in terms of a limiting distribution. And that is what we'll discuss today. So limiting distribution approach. So let us look at what happens for any consistent estimator. So suppose delta n is consistent. So if delta n is consistent, this implies that norm of delta n minus g theta goes in probability to 0 as n goes to infinity, which is equivalent to saying that if delta n is delta 1n, delta 2n, and delta mn, then delta imn minus gi theta. So there is a convergence in probability component wise. The two are equivalent, right? So because the two are equivalent, so I can talk everything in terms of a convergence of a real estimators. That means estimators which take only real values. So consistent in a sense, then in the real line it means delta n minus g theta goes in probability to 0. Now, so what it is happening in some way, this error, the distance between delta n and g theta is becoming smaller and smaller as n goes to large. Now here also the similar kind of a situation arises. You might have more than one estimators for which there is a convergence in probability. For example, if delta n is going minus g theta is going in probability to 0, then 1 upon root n delta n minus would also go to, I can multiply it by 1 upon root n, that also would satisfy this property. So here also it makes sense for which estimator this is going in probability to 0 at a much faster rate. So to show that, to see that, let us consider the similar kind of a situation. Suppose you have a sequence kn, which is kn is going to infinity. So suppose, let us not take any sequence kn. Let us take sequence kn is any sequence. So let us consider the following three scenarios or at least let us consider the following two extreme scenarios. Kn is bounded. If Kn is bounded and this happens, then you know that Kn times delta n minus g theta would also go in probability to 0. The other situation, extreme situation, could be Kn goes to infinity sufficiently fast. And in this case, what may happen is, under certain conditions, depending on how faster Kn is going to infinity, you might have Kn times delta n minus g theta goes in probability to infinite quantity. So it explodes. So as in the case of a limiting risk approach, so there is a possibility that, that there exists a sequence Kn such that Kn goes to infinity and Kn times delta n minus g theta goes in probability to some random variable y, and y has a non-degenerate distribution because, so let me emphasize that once again, y has non-degenerate. So note that convergence in probability to 0 implies convergence in distribution to a degenerate random variable 0. So what is being emphasized over here is there is a possibility that there is a sequence Kn such that Kn goes to infinity, but once you multiply delta n minus g theta by Kn, you get a convergence to a non-degenerate random variable y. Whereas convergence in probability to 0 means your distribution is degenerate at 0. Now certainly, if such a thing happens, this clearly implies that Kn minus delta n minus g theta goes in probability to 0. So delta n is consistent for g theta is clearly ensured by this condition. Why? Because Kn is going to infinity, so 1 upon Kn goes to 0. So if this is going in probability to y, so 1 upon Kn into this will go in probability to 0 by Sturskey's lemma. So what I try to look at is, I try to look at appropriate sequence Kn such that Kn times delta n minus g theta goes in probability to a non-degenerate random variable. So it is in parallel to what we did for the limiting risk approach. Now if that happens, this Kn may be considered as a rate of convergence in terms of a convergence in probability for the sequence delta n. So we say that if, let me call this as star holds, we say that delta n converges in probability to g theta with rate 1 by Kn, or we say that norm of delta n minus g theta tends to 0 with rate one by Kn. All right. One can also say that delta, if star holds, I say that delta n converges in probability to g theta at the rate 1 upon Kn. Okay, now let us look at the following examples. As we saw in the limiting risk approach, error rate is not unique. Error rate is not unique. Why? That means if two sequences are asymptotically equivalent, that means their ratio goes to some constant c which is different from 0 to infinity. So if error rate is 1 upon kn, and you have another sequence Mn which is equivalent to Kn, that means such that Mn upon Kn goes to a constant C which is 0 to infinity, strictly between 0 to infinity. And Mn goes to infinity, such that Mn goes to infinity, but Mn by Kn goes to C. Then 1 by Mn is also a rate. Why? Because to show that 1 upon Mn is also a rate, what you have to see? You have to see whether Mn times delta n minus g theta is going to a non-degenerate random variable or not. Now note that this is same as Mn upon Kn into Kn times delta n minus g theta. Now this is going in probability 2. Why? Because Kn is the rate. This goes to constant C. So this will go by Strutsky's lemma in distribution to C times y. Y is not a degenerate random variable, and C is a constant different from 0 and infinity. So Cy is also non-degenerate. So that is why Mn into delta n minus j theta goes to a random variable which is non-degenerate. So Mn is also a rate. Okay. Now what could be the other possibility? Error rate is 1 by Kn plus Mn goes to 0 at a slower rate than Kn. Mn goes to 0 slowly or faster than, Mn goes to infinity slowly or faster than Kn. What does that mean? That is, it goes to slower, that means Kn is going to infinity much faster. That means Mn by Kn goes to 0. And if Mn goes to infinity at a faster rate, that means Mn by Kn goes to infinity. Then what happens? If that is the case, then Mn times delta n minus g theta will converge in probability 2 by the same way. So now what is happening is, in this case, Mn by Kn is going to 0. This was going in distribution to y, so everything would go in probability to 0. And in the case where Mn by Kn was going to infinity, this is going in distribution to y, this may go to plus minus infinity. So what this says is, if delta n is consistent for g theta and Mn goes to infinity much slower than Kn, then Mn is also a rate. So Mn goes to infinity at a much slower rate means Mn by Kn is going to 0. So in that case, Mn into delta n minus z theta Mn by Kn. So what it suggests is, if delta n is consistent for g theta and delta n has a rate Kn, or error rate is 1 upon Kn, and if Mn goes to infinity slower than Kn, then the error rate is also 1 upon Mn. Okay, so this is the one. Now once we are talking about comparing estimators in terms of their asymptotic distributions, few things will come into the picture. So the following result, which you might have done in your probability theory course, would be useful. What it says is, yn goes in distribution to y if and only. First of all, what is the distribution of, definition of yn going in distribution to y? That means distribution function of yn at the point t goes to distribution function of y at point t, provided t is a continuous point of a distribution function of phi. Now, you saw that this is equivalent to saying that limit n going to infinity of expected value of psi of yn is same as expected value of psi of y for every bounded continuous function psi. Of course, we are talking about real valued functions. Now, what would happen is in many cases, so let me write down again as a remark, in many situations in star, that means when kn times delta n minus g theta is, sorry, this would be in distribution to y, not in probability to y. When kn times delta n minus g theta is going in distribution to y, a random variable, this y is normally distributed. So many cases you will have a limiting distribution as a normal distribution. So y is suppose normal 0 tau square theta, where tau theta is greater than 0. So in certain sense, what it says is the distribution of kn times delta minus g theta goes in distribution to normal 0 with variance as tau square theta. So tau square theta is in certain sense asymptotically measuring how much variation is there in kn times delta n minus g theta. So that means for estimator for which this tau square theta is smaller, that should be preferred. So this suggests that for large sample sizes, one can compare estimators through the limit asymptotic variance. So what I am doing now is I am just introducing few definitions. Let me write down over here. So if this is the situation, that means if your limiting distribution of kn times delta n minus g theta turns out to be asymptotic normal, normally this mean would be mean would be 0 because delta n minus g theta, delta n is an estimator of g theta, and there would be certain variance. Now this variance measures the distance between delta n and g theta, variability in delta n minus g theta. So for the estimator for which this variability is small, this would be preferred. So if variance is 0, that means delta n minus g theta has no variability. So asymptotically, estimators for which tau square theta is near 0, this would be preferred. So let me give the definition of our asymptotic variance. So suppose Kn is such that Kn goes to infinity as n goes to infinity, and you have a sequence of estimators Kn, delta n such that Kn times delta n minus g theta goes in distribution to normal with, let us say, mean as a theta and variance as tau square theta as n goes to infinity. And I take this to be positive. Now we have defined the limiting variance. Limiting variance is expected value, limiting risk is expected value of delta n minus g theta whole square. Limiting variance is limit of expected value delta n minus expected value delta n whole square. Now whatever is the variance of the limiting distribution, we will call such a variance as asymptotic variance. So if such a scenario holds, I call tau square theta as asymptotic variance of delta n, called asymptotic variance of delta n. Similarly, this A theta is called the asymptotic bias. So A theta is called asymptotic bias of delta n. Note that delta n I am using as an estimator of g theta, so it is biased in that sense. Now, if A theta is 0 for every theta, then I call delta n to be asymptotically unbiased. Then delta n, which is a sequence of estimators, is called asymptotically Now, if delta n is asymptotically unbiased, I call g theta to be the asymptotic mean of delta n. If delta n is asymptotically unbiased, g theta is called the asymptotic mean of g theta. So what this definition is essentially saying is, whenever we talk about asymptotic variance, asymptotic mean, everything we are talking in terms of an asymptotic distribution. That is what it says. So from this, we get the hint that if there are estimators, if there are two estimators for which k n delta n minus g theta has asymptotic normal distribution, then it makes sense to compare them in terms of A theta and tau square theta. So first of all, if delta n is an estimator of g theta, I would expect that A theta should be 0, because asymptotically they should be unbiased. Second thing, I would expect tau square theta to be as small as possible. So this, in certain sense, gives me a hint to compare different estimators asymptotically in terms of a limiting distribution. Now, the question is suppose you have a moments existing and you also have an asymptotic distribution, is the limiting variance is same as the asymptotic variance? The answer is no. So for example, this tau square theta, so the question which I want to pose is, because if that happens, then the two approaches turn out to be same, provided the moments exist. So the question is, limiting risk is same as or not asymptotic variance. Or in other words, can I say that limit n going to infinity of expected value of kn square delta n minus g theta whole square is same as tau square theta or not? Right? That is what is, that is if A theta is 0. So that for every theta. Then whether this is same as the asymptotic variance or not. That is what the question is. And answer, you know from your probability theory course, the answer is no. So this says answer is no. Now to see that, you can consider the following example. So suppose Z is normal 0, 1, and you have a sequence of estimators yn. Yn goes to normal 0 tau n square, normal tau n square. Yn is distributed as normal with mean 0 and yn tau n square, and tau n square is such that it goes to infinity as n goes to infinity. I define new random variable Zn. Zn is Z with probability pi n, and it is probability yn with probability 1 minus pi n. And I choose pi n such that pi n goes to 1. I intelligently choose pi n so that, so the idea is as pi n goes to infinity 1, this probability becomes 0. So you would expect that Zn is distributed as Z, which is nothing but normal 0, 1. So that means asymptotic variance of Zn will turn out to be 1. And then you try to show that, but its limiting risk will not be 1 if I choose tau 1 and pi n appropriately. So the idea is very simple. So first, to see the asymptotic variance, I try to see what is f Zn t, which is probability Zn is less than or equal to t. So what is this random variable is saying is you have a sequence Z and sequence Yn. At each occasion, you toss a coin. So on the nth occasion, you toss a coin whose probability of head is pi n and probability of tail is 1 minus pi n. So if on the nth occasion you get a head, you take random variable to be Z, or which is equivalent saying that you observe one value from normal 0, 1. Whereas if on the nth occasion if I get a tail, then I observe the value from normal 0 tau n square, and that is what gives me a random variable Zn. So let's look at what is the probability Zn is less than or equal to t. So that is same as pi n times probability Z is less than or equal to t plus 1 minus pi n times probability that Yn is less than or equal to t. All right, so this is same as pi n. Z is normal 0, 1. So probability Z less than or equal to t is phi of t plus 1 minus pi n. Probability Yn less than or equal to t is nothing but phi of t by root tau n, because Yn is normal 0 and variance tau n square. Where does this goes to? As n goes to infinity. As n goes to infinity, tau n goes to infinity. So this goes to 0, so this goes to half, but pi n is going to 1. So this whole goes to 0, pi n goes to 1, so this goes to phi of t, which is normal 0, 1. So asymptotic variance of is 1 by 1, right, which is the variance of the limiting distribution. Limiting distribution is normal 0, 1 in this case. Okay, now I try to see what is the limiting variance. So for that, first try to find out what is the expected value of Zn. Expected value of Zn would be nothing but pi n times expected value of Z plus 1 minus pi n expected value of Yn. Expected value of Yn is 0, expected value of Z is 0, so this is 0 for every n greater than or equal to 1. What is the variance of Zn? Variance of Zn nothing but expected value of Zn square, which is nothing but pi n times expected value of Z square plus 1 minus pi n times expected value of Yn square, which is nothing but pi n times 1 plus 1 minus pi n times expected value of Yn square is nothing but tau n square. So the thing which I want is this should not go to 1, because asymptotic variance was 1. Pi n itself goes to 1. So that means if I could find that 1 minus pi n tau n square does not go to 0. But the pi n and tau n have a condition that pi n goes to 1 or 1 minus pi n goes to 0 and tau n square goes to infinity. So this goes to 0, this goes to infinity. So I want that the product, this goes to infinity, this goes to 0, but the product should not go to 0. So that is very simple. I can take 1 minus Pn to be 1 upon n, and tau 1 squared to be n. So this goes to 2 for the choice pi n is equal to 1 by n, and tau 1 square to be no. So what I want, so what you expect is, so yeah, pi n has to go to 1, so pi n I take as 1 minus 1 by n. So 1 minus pi n becomes 1 by n, and tau n I can take as root n. Then it becomes 1, so it goes to 2. So which is not same as the asymptotic variance. So in general, the asymptotic variance may not be same as the limiting risk. So the question is, what is the relationship between the two? And this again could be a part of Fatou's lemma. Let me not state that, let me not prove that result, but let me just state so suppose yn is kn times delta n minus g theta, which goes in distribution to y as n goes to infinity. Then limit infimum of expected value of yn square would always be greater than or equal to expected value of y square. So what this would say in general is limiting variance is always greater than or equal to, this would be kind of a limiting variance if I center y is always greater than or equal to asymptotic variance. So in that sense, the two approaches are not same, even if the movements exist, even if you can talk about limiting x. Now the equality here would hold if yn is some function of hx bar, and this h has bounded kth order derivative. For some k greater than equal to, of course in the IID case, right? So IID case. In general, they will not be same. So you can, one can look into various results of this kind, but since we are talking about limiting variance and limiting risk, these are natural questions which may come to somebody's mind, and that's the reason why I stated this result. So what we are going to see is, in many situations, our estimators are such that when I normalize them, the asymptotic distribution turns out to be normal. So if you have two estimators for which after normalization the asymptotic distribution is normal, I can compare them in terms of their asymptotic variance. First is in terms of rate of convergence. The one for which rate is going to 0 at a much faster rate should be preferred. But for the estimators which have the same rate of convergence, the one having the smaller asymptotic variance may be preferred. So that we'll discuss in the next lecture. So this is where I would like to stop for this lecture. So next lecture will further develop various methods to compare the estimators asymptotically. The background we have discussed today already. So thank you. See you in the next module.